If you were to draw the graph for wait, this and that, okay. So if they ask you to draw the graph to draw the graph of the energies like this, like in recent years, they usually give the graph like this, okay, like this, okay, right. And let's say they told you the amplitude x naught and x naught, okay. And you know that at amplitude, there will be maximum gravitational or just potential energy, and at the mean position, there will be kinetic energy, right? Mm, where should I find the scale? Okay, so this is more than 6.567, 6 point. Okay, it should be what? Somewhat right here. Okay, 5.7 पे. So would be at this point. Okay. Now, so x naught and okay. So if we draw the graph for the gravitational potential energy, so let's say for the total energy, let's say this is the graph for the total energy, let's say, okay. So and you know that the total energy will always be conserved in a system. So none of the graph will be um like the potential and the kinetic will be more than that or greater than that, okay. Now if we try to draw, okay, graph should be right here, okay. So this is actually important because you have to start the total energy graph from exactly the point where the amplitude is maximum, okay. Now the gravitational potential, the potential energy will be maximum when your height is maximum, and it will be minimum when you are at the mean position, right, like this. Oops, what the hell, man. Okay. Mm-hmm. Okay. And right here and right here. Okay. So this is the potential energy graph, gravitational potential energy. Okay. And the graph for the kinetic energy will be maximum in the at the mean position and minimum at the ends. So it will be like this. Okay. And in the previous class, we work out this position. Okay. This is the position where kinetic and gravitational potential energies are equal. Your potential energy are equal. Okay. So this is the point where both the energies are equal, right? This is the point where both the energies are equal, right? So kinetic and potential are equal at this point, okay? And we know that on the amplitude graph or on the displacement graph, this position is basically 0 point, sorry, 0.707 of x naught, right? Which we did previous in the previous class, right? Like if the displacement of the oscillation, the displacement of the oscillation when the kinetic energy is equals to the potential energy, right? Now that's done. This is like frequently asked question. Now This is one of the scenario that was missing. Now, I have, after this scenario, I have the concept of the damping and the resonance, okay? Or like the forced oscillation. Previously, we understand all the concept of the free oscillation, and now we have to, now we have to discuss the concept of the forced oscillation, okay? So, forced oscillation. Okay. So from this point on, we have to do the forced oscillation. Right here. Okay. Forced oscillation. Yep. Okay. So in forced oscillation, it is basically the concept where the oscillation is done under the influence of the resistive forces. Okay. So it is the oscillation under the influence of resistive resistive force. Okay. So this is a concept. This is the forced oscillation. Okay. And forced oscillation are also known as the damping. Okay. Like, so the forced oscillation is basically the oscillation under the influence of resistive force. Resistive force. Okay. And this concept is basically this concept of the forced oscillation and the cause of the forced oscillation are known as the damping. Okay. So the second thing is the damping, and damping is basically the energy loss, by the way. Okay. So it is the damping. Okay. So damping is basically this is the name of the concept where where the resistive force causes the loss in the energy of the oscillation, right? So you know that in AS level when where you do practicals, okay, so you oscillate a pendulum, and the pendulum after instead of time it gets stopped at its original position or mean position, right? And that is because of the air resistance or air present in the room, right? So the pendulum have to do the work done against the air as well, as it is moving, right? So all of its energy, total energy, convert into the work done against the resistive forces. Okay, so damping is basically the um, loss in the amplitude of the oscillation, okay, due to due to the resistive force. Okay. And this causes the energy loss, by the way. Okay. This causes the energy loss. Okay. So you cannot directly observe the energy loss, but the energy loss is basically related with some things, and these are basically the concept of damping, right? Where you can see the amplitude is not the same as the amplitude of the previous oscillation. So you can say that the amplitude is decreasing because of the decrease in energy due to the presence of the air resistance called damping. Okay. So is that clear, guys? Okay. So by the way, damping have three type, which I am going to copy paste right here.
So this is the low damping and the
Mm.
this is low damp. One of them is low damping, right? Or is
Um, Light damping, not low
Light,
damping.
yeah, yeah. Okay.
Okay, so copy and paste. Okay, paste. Whoop. No, back. Oh, back. So this is right here. Okay. So the first one is, so these are the type of the damping we have. Okay. So the first one is the light damping and the critical damping and the heavy damping. Okay. By the way, please keep in mind that damping is basically it reduces the efficiency of the system, right? It is the loss in the energy. Okay. It causes the loss in energy, right? So So these are some of the type of the damping. Okay. So the first is the light damping, which is like asked 100 times in the paper. Okay. And they are like, if you have to define it, so it is basically the gradual loss in the energy, gradual loss. Okay. It is not the abrupt loss. It is a gradual loss in the energy of the oscillation due to the presence of the resistive force, right? Now, Um, so if you have the original graph without the damping, so this graph look like this, right? The one with the amplitude not changing, okay? But the other graph, you can see that the amplitude is changing as it is moving, right? So this is basically the damping graph, okay? They ask you many time to draw the damping graph, okay? To draw the damping graph on the actual graph, right? So you have to draw it like that. Okay, they'll give you 3 mark, and the 3 mark for the new amplitude should be smaller than the previous one. This is the first mark. The second mark would be time period should be approximately same. It should not be changed, right? So you can see that both the oscillation ends right here. Okay, and then the third thing is consecutive decrease in the amplitude, right? So the first amplitude was right here, the second lower than that, the third is lower than that as well, right? So this is something that they want you to show in your drawing. Okay, so this is basically the light damping. Okay, now after that we have the critical damping. Okay, and critical damping is basically when you make when you make a system where you want to lose the energy of the oscillation instantly, okay, without even completing a single oscillation, right? So that is basically the critical damping. Okay, so and you can see the graph. Okay, the graph isn't completing a single oscillation. It's just it is just damped as soon as possible. Okay, and this is mainly placed or situated in the car suspension. Okay, where you want the car to stabilize as soon as possible after moving past the speed breaker, the hump, or any like unevenness in the in the road. Okay, and then after that, we have the third case, and where we have the heavy damping. Okay. And in the heavy damping, um, we reduces or we make the loss in energy in the longest amount of time. Okay. Critical and heavy damping are basically the artificial damping, but the light damping is like the natural damping. Okay, in every oscillatory system, you will find the light damping in that, right? But critical damping and and heavy damping are something that we introduce in the oscillatory system, right? Now, um, mm, okay, if you look at the graph of the heavy damping, so heavy damping, the graph of the heavy damping is basically very long. Okay, and this is because it required a lot of time to get back to its original position. Okay, so and you can use in the door stoppers, okay, these type of things. Okay, now this is one concept of the damping. Okay, so these are the type of the damping, right? Now we also know that the damping causes the loss in the energy, right? But if and we also know we know that the damping will be there in every type of system, right? You cannot make a system with no damping in it. Okay, this is approximately not possible, but some electronic system can be like that. Okay. So to overcome the damping or to overcome the loss in the system, we apply some external forces or some external frequencies or some external energy that maintain the energy of the oscillation of the system, right? So this will make us or this will do better for like if you want to continue the oscillation. Okay. And the concept is known as the resonance. Okay. I wish you have heard of the concept of the resonance. Okay. I'm also going to copy and paste it. Right. Copy and paste. Since it required only contain the theory concepts, so that's why I'm pasting. Whoa, man. Copy and okay. So to overcome the damping, the effect of the damping, we use the concept of the resonance to overcome it. Okay. So the concept says that when the natural frequency become equal with the forcing frequency, the amplitude of the system will increase efficient and the efficient energy transfer take place. Okay. This is the concept of that resonance. Okay. So resonance required a natural frequency and the forcing frequency to be same. Okay. And then after that, you required the amplitude, like you can see the energy transfer with a variation of the amplitude, right? Because you cannot see the variation, the transfer of energy without the change in the amplitude. Okay. It's not possible for us. So resonance has the same concept. Now we have to understand the concept of the natural frequency. Okay. Natural frequency is a frequency with which an object oscillates. Okay. If let's say something is stationary and you make it oscillate, okay, so the initial push that you provide to make the object move and the object is now oscillating, so that frequency with which the object start oscillating, that frequency is basically known as the the natural frequency. Okay. So the frequency with which something is oscillating or it is made to oscillate. Okay. So this is the first concept of the natural frequency, right? Now, the forcing frequency on the other end is basically the frequency that you applied on the system, right? And as soon as you apply the frequency on the system, the freq the system will start moving or start doing efficient work energy, um, or efficient work or energy transfer, right? Now, the forcing frequency should be equal to the natural frequency. Why? Because if they don't equal, if they won't, if these two things won't be equal, then the energy transfer won't be take place, or maybe may not be like transferred at all, right? So you can imagine a swing that just move back and forth, okay? And let's say somebody is sitting on it, and he asks you to push to some distance so that he start oscillating, okay? So your first push, which make the person sitting on the swing start moving, the rest of the rest of the oscillation will have approximately the same frequency, and that frequency is known as the natural frequency, right? Now, after every oscillation, if you try to push it with a forward push, okay, to keep him in the oscillation, so that external push from you on the person sitting on the swing is basically the forcing frequency, okay? So when these two things matches, okay, you'll have the greater efficiency, greater energy transfer, and efficient energy transfer and greater amplitude, right? There are some example of there are some example of the application where we have or where we use resonance concept. Okay, one is if you hit the if you keep the chocolate in microwave, okay, and you just start it, so you can see that the microwave distribute the chocolate into the superposition form, okay, and that is because of the resonance, okay. And similarly, if you put the food in it, so it will again heat up the food for you, okay. And that is because the liquid content, the water content in the food is basically oscillating or vibrating, okay. So if they're vibrating or oscillating, so they'll have their own natural frequency, right? And when you apply the external frequency using the microwave, okay, so it will again so that external frequency basically agitate the the actual particle, and the efficient energy start transferring, okay. Now the second and the third thing are not actually the part of the syllabus. For second thing are not the part of the chapter basically, but the part of the syllabus as well. But the third thing is not the part of the syllabus. Okay, but you should know that the generation of the ultrasound in the transducer and the generation of the transducer in ultrasound. Okay, so yes. Now we will learn the concept of the ultrasound and transducer in ultrasound chapter, right? Now we have the graph. Okay, so these are the graph for the for the resonance, okay. And like they'll ask you many time this type of graph in the question, okay. And the concept or the reason for this graph is mm, that you should be able to make the oscillation with oscillations amplitude with respect to frequency. This is the first thing, okay. And then you should be able to show how the natural oscillation look like, and how the natural oscillation mean free oscillation, okay. Free oscillation looks like, and how the forced oscillation look like, okay. Now, so the first graph is basically the free oscillation, and you can see that the free oscillation does not have any ending of the amplitude, right? Because if you just keep pushing the system, so it will go to infinity, right? So, yep. Now, the second thing is, wait. Now, the second thing is the damping graph, okay. But we have, but in this case, we have the light damping, like not that much hard damping. These are not the graph for the light or critical damping or heavy damping. But in the second case, where I draw the line with a dark green, okay, is basically showing the slightly damped system, okay, which you want to resonate, okay. So due to the resonance, it is ending at some point, okay. And the peak of the system is basically showing that. And on the y-axis you have the amplitude, okay. On the y-axis you have the amplitude, which means when you apply the frequency, the amplitude of the system will start increasing, okay. And similarly, but for the other case where you have the where you have the resistive forces present, so it won't carry that much up, okay. And if somebody asks you to if they ask you to draw the graph with a increased damping, right, so you should be able to draw the graph like that, okay. Now one more thing, and that is if you want to um let's say, okay. So one more thing, and that is if they ask you to write down the natural frequency or the forcing frequency, so basically both should be at the same point, okay? When the natural frequency and the forcing frequencies are going to be equal, okay, then the resonance occur, right? So at the resonance, at the resonance or on the resonance, you just keep up with one of the frequency, and the other will be some multiple of it or something of it, okay. So yes. Now these are all the points that we have discussed in this chapter, okay. And the simple harmonic motion chapter is now completed, okay. So Let's try some of the questions. Okay, just give me a second, please. Okay, so let's do some of the questions. I have the past paper with me. Okay, let's try this one. Okay, can anybody read the question, please? Iran, can you please read the question?
Uh,
Hmm.
a small steel sphere is oscillating vertically on the end of a spring, as shown in figure 4.1. The velocity v of the sphere varies with displacement x from its equilibrium position to according to v is equal to plus minus 9.7 square root of 11.6 minus x square, where v is in centimeters per second and x is in centimeter. Calculate the frequency of the
Okay, any idea why? If you guys remember, we did a formula where we say that v is equals to v omega and root. So we did this formula, right? So we know that omega is basically 9.7. Okay, omega is basically 9.7. Okay, so and we know that omega is basically 2 pi f. Mm, come on. So f is equals to 9.7 divided by 2 pi. How much? Yes, guys, how much?
15.23, sir.
Okay,
1.54, sorry.
1.54. 1.54. Okay, fine. What about show the amplitude of the oscillation is 3.4? Okay, so amplitude squared is basically x naught squared, okay, is equals to 11.6. Okay, so it will going to be 11.6 and then root, right? So are you getting? Yes.
Yeah, I'm getting 3.4. My mic was muted, sorry.
3.4. Okay. 4. Good. Now calculate the maximum acceleration. You guys know that the maximum acceleration is a formula of x naught omega squared, right? We already found out that x naught is the amplitude, which is 3.4, and omega is basically the 9.7. Okay, so you can square it, and you can square it. Okay, so you'll find out the acceleration. How much?
319.9.
319. So 320. Okay, fine. Now, if mm, fine. Wait. Are you guys sure it is? Wait, wait, wait. Didn't we convert the centimeter to meter? Oh my God, sorry. So you have to do conversion exponent negative 2. So 1, 2. So it would just be 3.2, right? 3.2, right. Okay, now on the graph, they're asking you to draw the acceleration graph. Okay, so we know that the amplitude is 3.4 and that we have to be careful. Okay, they're giving you 3 marks. So 3.4 is the amplitude and acceleration is 3.2. Okay, so 2 and then 2.2, 2.4, 2.6, 2.8, 3.2. Okay, and 1, 2, 3, 4, 5, and 6. And this is the A naught. This is the graph that you have to make. Okay, so this is how it should look like. Okay, you're not allowed to make the graph of all the way from one point to another point. Okay, okay, please move on. Asha. So for this one, we know that at amplitude, um potential energy will be maximum. Sorry, maximum, and at mean position, PE convert converts into Ke, right? Second, and then at x is equals to 0.707 of x naught, which is the 70% of the amplitude, the change in kinetic energy should be equal to the change in GP, right? So this is the concept, right? Clear, guys? Okay. Now I think that's it. Okay, I'm stopping the class right here. Okay, now we'll do the questions in tomorrow's class. Okay, we have to do the whole tomorrow class for the question. Okay, and then we'll be done with this third chapter. Okay, so I am ending the class right here. Okay, and there's an namaz time as well. So yep, that's it. Done. Okay, guys, take care, Bachu. Allah Hafiz.
Love is
Allah
After
Hafiz. Allah Hafiz.